Oh. Well, again, welcome and good morning or good afternoon, everyone. So my name is Yu Ding. I'm a faculty member of Georgia Tech, and I see many familiar names or faces. And many of you have been with this series for nearly a whole year. So today we're going to have Ahmad, a graduate student at Georgia Tech, to give a simple analysis we did in the past couple of weeks. Try to see what if you use met tower measurement, reverse engineer the power curve, and to see that will improve the estimate of the nacelle anemometer wind speed measurement or not. And this is one of the issues we discussed earlier in the year. And we said that, for the performance evaluation, we can sort of separate this two problems. One is how accurate the wind speed is measured, and then assume the wind speed is accurately measured, and how much you will use that together with other environmental condition to control for and quantify the power change and attribute that to the wind turbine itself, excluding the impact of the external impact. Okay, and before Ahmad gets started, as we scheduled the monthly meeting, after the new year, our next meeting was originally scheduled on January 13th, which is a Monday. And I know different folks have different holiday schedules, and oftentimes the January meeting is hard to make. So I'm going to cancel the January 13th meeting, and we're going to meet after the new year in February. I think that's going to be second Monday in February, February 10th. And then afterwards, March 10th, if it's needed. So I will make that clear in the email I sent after the meeting, and also share the recording and the slides. Okay. So without further ado, and Ahmad, and the screen is yours.
Sure. Thank you. Excuse me, Professor. Could you please let me know if the slides are?
Yeah, looks good.
Okay. Hi, everyone. My name is Ahmed Chokhachian. I'm the PhD student in Dr. Yu Ding's team in Georgia Tech. And recently, we worked on a problem within a couple of weeks. The topic of this meeting is estimating free stream wind speed using machine learning models. So in a wind farm, so far we usually use the NASA recorded speed data, but we know that there is problems with it. One is the weight effects of upstream turbines, and the other challenge is flow distortion, because the nozzle is located behind the blades, and that really affects the data. So we looking for somehow estimating the free stream speed on each one of the turbines, but we have two key assumptions. One is like the met tower measurements compared to the nozzle measurements are less affected by the wake effect. The other assumption is like in a wind farm, if the turbine is so close to the one of the met towers, then that met tower is representing the free stream wind speed on that turbine. So by these key assumptions, in case we have a ideal wind farm with one met tower beside each one of the turbines, then we can simply just use free speed on the speed recorded on met tower instead of nozzle speed. But there is an issue here. Usually in wind farms, we don't have more than a few met towers. In most data sets we have, we have only one tower for the farm. So This is not gonna happen, and we don't have that many towers, so we're looking for forward to see if we can build a model to create a inverse power curve function on one tower and turbine set, and then we can use that model to make predictions of the free speed and different turbines. But to do this, we really at least need two towers beside two turbines. So we can create a model on one set and then validate our machine learning model on the other set. The ideal data set for this work has some requirements. One is we need at least two Met towers, but if we have more, then we can validate our work more. Maybe we can come up with better models, but at least two towers are required. Also, uh, for those two towers, there should be turbines very close to them. So if we have a tower, but there's no turbines around it, so we cannot really use that tower's recorded speed as free stream on any turbine. So that tower will not be useful in this work. The other requirement is the data. So features we at least need is nozzle recorded data and also power generated power by the turbines. Also on the Met tower, we clearly need the speed recordings. But this is required, but it can help us to further improve our work in case we have more features like rotor speed, yaw angle, blade pitch or etc. Uh, in today's work, we really do not have those features, but we'll discuss it more in the next slides. So the key steps of our model is the first, we filter the data to just keep the data points between the cut-in and rated, because in that region, there's a monotonic relation between speed and power, and usually creating an inverse power curve function is easier for that region. So the second step is fitting the inverse power function. The input of this model will be power one. Power one is on the modeling set, the generated power by turbine one, and the output of this model is not the nozzle data, but the free stream wind speed coming from the tower one. Tower one is the closest Met tower to the turbine one. Then we use this function, this model, to predict for the validation set. In the validation set, we can use the power of the turbine 2 and then estimate the free stream speed on that set. Then the big question is which one represents the free stream wind speed better? The estimated speed of this model or the nozzle data? So to evaluate that, we just formed the RMSE of these these three variables: free speed and nozzle speed, free speed and estimated speed. And clearly, if the second RMSE, the free speed and estimated speed, is smaller, that means estimated speed is closer estimation of the free speed compared to nozzle. So this is our approach, but the only data set we have tried it and so far is EDP data set, because this was the only data set we had more than one towers in it. So we could really create the model and also validate it. So in this data set, there's 4 Met towers and 240 turbines. Like half of the turbines has 4 years of data and the other half has only 3 years of data. So there are some issues with this data set. One is that it really has only power and air density from the turbine data, SCADA data, that we can use as the predictors of our inverse power curve function. So as I discussed, meaning like three slides before, it's really desirable to have more variables like rotor speed and etc. But in this data set, we really don't have those data. The second feature is like Met Tower has some periods of missing data. So if it was missing data points with timestamps, we could probably impute them. But as it's really a period, it's shown in the green by green in the figure. There is like two gaps in the data. So those periods cannot really be imputed easily. So for this model, we need to match the timestamps of the Met Tower and turbine. So at the end, our data will become smaller because of having these missing periods. And finally, we also take a look to the distance of the turbines closer to the tower, Met Towers, and all four turbines that are the closest to the towers are within almost 200 meters. So they are pretty close. On the implementation side, we have a few steps. So first, we match the timestamps because we will create a model which input is coming from turbine data, but output is coming from the Met Tower data. So the timestamps needs to be the same. Then we drop the missing data periods from both of them. And then we have a filtering step which just keeps the data between cut-in to rated speed range and just excludes the other periods, other speed ranges. And then finally, for the modeling, we use twin Gaussian process. It's actually well known for large data sets, and it has competitive accuracy over all Gaussian process methods. But in next slides, we actually have a sensitivity analysis on this model. So we're gonna see what if we choose different models, how much the results will be different. So initial result we gained was almost 22% better estimation by the model. So here, the modeling turbine and Met Tower is the one on the northwestern side of the farm, and the validation is the set in the south. So the model's prediction and free speed RMSE is 2.18, and nozzle and free speed RMSE is much larger, 2.66. It's a 22% difference over there. So, but then we decided to also take a look to not overall RMSE of the whole data points, but a moving RMSE. So in the plot, we see really twin GP models RMSE. The green line it has a gap with the red line, which is nozzle RMSE over 2 months moving RMSE. So this was a good result, but then we tried to change the modeling and validation sets. So this time we modeled on the turbine and Met Tower in the south, and then validated it on the set we have in the northwest western side of the farm. Here it's almost consistent. There is 18% improvement over nozzle recording if we use this model. So so far it's 18 and 22% improvement gained by this model. But then we decided, so in this wind farm, we have two more towers. The data period is smaller, but still we can try and see what numbers we get with this method. It shows for those two turbine and Met Towers, the gain is huge. So from 22%, 20% range, we get 40 and 55% gain over these two validation sets. So it still seems like this model has a severe gain. But there's some further questions. So as we discussed, more covariates for the machine learning model, a better fit we can get. So Here in this data set, we only have power, standard deviation of the power, and air density as the covariates that we can use as the input variable of the inverse power curve. So the numbers I show so far was only using power, but we'll see what if we add those variables. Then the second question is how much sensitive is our work to the choice of machine learning model? So what if we use XGBoost, random forest, and other models? Then so one step we had was filtering the data. That's actually a big help to this model because when we don't filter the data, it's really harder to cache the inverse power curves uh, uh, dependencies. And here we'll see what if we don't do that filtering. And finally, the last question is, what if we use more than one turbine and met tower set for training? So we saw training in one set, testing in one set. We saw training in one set and validating in multiple sets. But the next, in this question, we'll see what if we train on multiple sets and test on one turbine and met tower set. So to answer the first question, here in this table, we have three different trials having only power as input, having power and the standard deviation of power, having power and air density. There is not really a significant change over these three trials. But still, we think maybe having variables like rotor speed might help. The second question was the choice of machine learning model. So we have tried different models here, from neural network model, a simple feed-forward one, TempGP, a Gaussian process which accounts for temporal dependencies of the data. TwinGP is known for being fast on large data sets, but in this work it shows that it's also has really good accuracy. Then random forest and XGBoost. XGBoost is even better than the TwinGP, but because of that small gain, I had a big grid and tuned the XGBoost hyperparameters over that grid. So maybe TwinGP does not really have that many parameters, and I really did not any tuning. So TwinGP is faster and has a competitive accuracy. But in the future, someone may decide to either use XGBoost or TwinGP. So the next question was the effect of filtering. So as again I said, we have only power as the input of inverse power curve. It's super challenging to capture the regions where the relation between these two covariates is not monotonic. So we expected to have worse prediction accuracy by not filtering, but still, if we do not do the filtering, there is 6% gain. That 6% gain still makes us hopeful to use this model, and maybe by having more covariates, we can enhance even if we do not do the filtering. And the next question was, what if we train it on more than one data set? So in the previous work, we had it modeling training on only the turbine and met tower set on the northwestern side of the farm. But now in this experiment, we train it on multiple data sets. So we have three of them for training, and validation is on the last one. So it shows feeding that large data to the model not only does not improve the accuracy, but also has a drawback, and we lose some of the prediction accuracy. So here it was 2.18 as we see in multiple slides. By including them, there is a rise in the RMSE to 2.13. it shows like maybe in the next future wars we can just rely on one met tower and turbine for training. And finally, what we discussed here was the choice. The machine learning models can help us estimate the free stream wind speed for turbines, and the estimation will be at least more accurate than nozzle data. But the difficulty we had in this work was only having power as the input feature, and it really limits our ability to fit a very accurate model. So having more covariates like yaw angle and others might help to gain a higher accuracy for the inverse power curve model. And in this work, we did not have that, but if you have a data set with at least 2 met towers and like more than and also including those features, we would really appreciate if you can share it with us. Then we can try this method on new data sets and see if we can really extend this analysis on different data sets. Thank you for your attention.
Okay, thank you, Hamad, and for the presentation. And so we open the floor for questions and discussion. Well, it's a relatively simple idea. I'm sure other folks tried that before. I'm not really sure anyone really bothered publish it up in a paper or something. We didn't really do a very extensive literary review. Now, technically, as long as you have one turbine close enough to a tower, you can do something like this. But in order to demonstrate the benefit, you need to have 2 towers on the wind farm. Otherwise, even you do something better, you wouldn't really know how much improvement you made because you need to have some kind of new ground truth help you to benchmark. And that is the part we struggle, right? We have multiple wind farm data, but this is only one, I worked with EDP North American nearly 12 years ago, and this is the very first wind farm data I received from them, and it has a 4 met tower, all functioning, and that's why we decided to give it a try. And here's the result, right? I'm not sure if you had a similar experience, you try quantify the benefit from doing this, or you even have other, like Ahmad mentioned, turbine-specific variables like rotor speed, which should give a more accurate reflection of the wind speed because it's more directly linked to the blade, the rotor. Right. Well, any comments or questions? And
yeah, this is Brian.
Okay. Go ahead, Brian.
Yeah, this is Brian Kramek. I'm currently with DNV, but I've worked for several companies in the wind industry. One of the things that, if you go to your slide, it talked about whether or not to do the whole curve or the filtered curve. As part of that filtering, did you filter to valid wind sectors?
No, I don't think Ahmad aware of the valid wind sector. That's a wind direction question. No, the answer is no. Yeah, we can give it a try. The valid wind sector roughly about 1/3 of the entire direction. One of the reasons we didn't really do that in the initial try is really in order to generate the wind speed you can use for the entire operation scenarios. There's many times you don't really want to only compare with under that 30% of the condition. Right.
Yeah. So one of the things to keep in mind when you don't filter to the valid wind sector is that change in position, and that your test turbines will become waked, or your met mass will become waked by the test turbine, and that greatly changes the relationship. So what we found is that filtering to the valid wake sector gives you that it is still free stream at both places, at your met mast and at your turbine, and that would still apply in other locations. The other thing is that you had talked about, Ahmad, you talked about whether or not to use the full curve or just the part of the power curve, right?
Yes.
So one of the things you'll note once you have a little bit more data is that there's almost it's almost worthwhile building different different models from when the turbine is running to the turbine offline, actually looking at that data set for turbine power equals 0. But then you don't have, because what you'll see is that all of a sudden your anemometer, depending on the nacelle position, starts to be able to read the free stream better under those conditions. So it's actually a different relationship. It's not a linear relationship that a lot of people will apply for this type of work. So that's something else that might help improve your, is to actually separate the models between online and offline.
So Brian, do you guys have for example, a procedure published somewhere to give either a kind of like an algorithm or procedure to follow, or kind of guideline to follow from a DNV point of view?
Yeah, I don't think we've got anything yet, but that's one of the things we're going through a kind of a step change in our processes right now, and we're cooperating and coordinating a lot more with clients, and that's something that can definitely be done. I might actually just see if I can do this exact same presentation with a different data set. Are you aware of any other data sets that have the parameters that I would typically use include blade pitch and the nacelle wind speed? So this data set, you said you did have speed, but you don't have pitch, correct?
No.
Okay. So
We have a direction. We have a direction. We can ask Ahmad to organize the data and find a way to share with the participant here. We don't have pitch, we don't have yaw, we don't have rotor speed.
Yeah, and just as anecdotal information, some of the best models that I've built actually haven't been with machine learning, but with statistical models using the generalized additive model. If you're familiar with that package, in Python, it's called Pygam. But that allows you to have multiple nonlinear inputs to your model. So you can include blade angle pitch, you can include wind speed, you can include the wind direction at both the measured location, the turbine, and your met mast, all as your input variables, all as your predictors for what that wind speed is at the met mast, what the free stream speed is. And the generalized additive model has been a very strong contender. I know that NREL, a friend of mine, Mike Optis, that runs Veer Renewables now, when he was at NREL, they did quite a bit of testing on different types of models, and the generalized additive model family was always in the top for the types of models that are simple. They're easy to understand graphically, so you can actually see what's going on with your data. It's not quite as black box as a lot of the machine learning methods. So it's worth investigating. And that Python library is called Pygam.
Yeah, we call this set of model machine learning model. They are not really that much different from statistical models, right?
Okay.
Like the Gaussian process model. They are probably a little bit more complicated than the generalized additive model, but they offer some quite bit of similar features, and they are not as complicated as a deep learning model.
Yeah. How do they do as far as interpretability, human interpretability? Are they easy to understand graphically for the result sets?
There are other methods to help, in itself, there's a certain kind of parameters you can read into that. There are also other kind of toolbox you can use to indicate, which variable is more important, which one is more. But in this case, we only have one variable, so it's
right. Yeah, it makes it hard.
Right? Yeah. Christian, yeah. Thank you for waiting. Yeah, go ahead.
Yeah, thank you, Ahmad, for the presentation, and thanks also, Brian, for those interesting comments. You actually asked some of my questions already, but one last thing I had in mind was this result that the training on multiple turbines didn't help. Could it be just kind of by statistical chance that in this case the two turbines that predicted each other were more representative of each other? Because I suppose in this type of scenario, you're kind of relying on a certain degree of representativeness, and as you go kind of as things change across the wind farm that is not part of the model, the predictions would get less good. And I suppose a significant challenge is on validation, because it's hard to find a lot of data sets with multiple power curve tests masts across a site. But do you think if one were to build this for other sites, it could be that actually it helps to use multiple training points rather than not? Or do you think that there is a good reason to believe that it should be sufficient to train on one data set?
What do you think, Ahmad?
I just have one thought about data size. So for just one set, it becomes, for 4 years after pre-processing, it becomes around 200K data points. I'm not sure if we, on one variable, we include more and more data points, it will capture a better model. I think that size of the data is too large for just having one variable, but not really sure.
Christian, I think to your point about things changing over the site, one of my questions about whether or not they filtered to the valid wind sector. I think that when you look at the exposure of these, you've got one of the turbines is from the north, because this is a bimodal site, right?
that will make
Bimodal wind distribution.
a big difference. Yeah.
And then the other ones are southern. And if they didn't filter to valid wind sectors, as you add more, there's more noise from the backsides, of each one. And I think that probably confused the model.
Yeah, there's a two force here, right? One is you triple the number of data points. Generally, the more data points, the training data points you have, it helps. Another one is like for each pair of the turbine and the mat tower, they have somewhat different relationship. So when you put this kind of data set together, you sort of kind of get an average model rather than any specific model for this pairwise measurement. Now, for the type of data model we use, the TwinGP, right? Actually, we from our own experience, other than deep learning, most of other traditional machine learning or statistical model, when you use tens of thousand data point, right? You double that, triple that, the benefit is not there anymore. So the data point by tens of thousands is large enough. So if you, for one pair of this turbine and a mat tower, we already have 1 year data point. That is about 30,000 data points. So it's large enough. What I'm saying is that by tripling that size, it doesn't really bring too much additional benefit for the traditional machine learning model anymore. But on the other hand, once you put this kind of data set together, you invariably only learn one of the model, which is average. It's not really close to any of the pairs. And probably, it's just my guess, right? The specific relationship between one tower and one turbine would be the relationship to be used rather than average with 3 different pairs. And I even have the feeling, even you filter out the valid wind sector, that's probably going to be the case. So, which means the valid sector based learning outcome for one of the pair of the turbines will give you a better result rather than 3 pair to put together. We can give it a try afterwards. And we try to get the data and release, then you guys can try that as well. And so that way, we can we call this a collaboration, right? Because you have ideas, you know how to try that, and we can do that as well. Okay.
Yeah, I suppose that's if you, unless you have you capture the driver for the differences, you're right. You'll just have an average model.
Yeah.
Otherwise, if it's driven by, I don't know, let's say by example, it's driven by turbulence, then if you have turbulence as an input to the model, then that might help. But if you don't have it, if you don't have the driver for the differences across the site, then I suppose you. But
Right.
maybe the bias could be lower if you average more.
You probably, in that case, you almost like still train an individual pair relationship, but you use 3 pairs, and then you choose which one to use, right? It's like 1, 2, 3, and then in the southern one, it's like they have matched the third pair the best. I will use that relationship. But once you put 3 together, you still have one average model, which is not really just, it could coincidentally become the average model is the same as the pair 2 model. But that doesn't really guarantee to happen. And they could be deviating from that individual pairs with additional bias. Right. I think Chandra Moli has his hand raised, please.
Yeah, thanks for the presentation, Ahmad. It was nice. Just expanding on the previous points stressed by Christian and also addressed well by you. So I feel one of the other drivers that drives the relationship between the free speed and the relationship and the wind speed of the turbine is terrain. Maybe that's terrain effects are they can drive. So I just want to know from you, and just maybe thinking out loud with you. So if we want to include the effects of, say, terrain in this, so what would you propose? So we propose having one set of coefficients or one type of model for one type of terrain, and then if you want to use it in another wind farm, you use that, or you modify the model, somehow retune the model. How do you propose we can include the effect of other drivers like terrain or turbulence or something like that? Just thinking out loud.
You ask a good question. I'm laughing is because I'm smiling because Ahmad has one of the side project is working on the terrain effect on the power curve. And we actually published a paper last year in IEEE transaction on sustainable energy. And in publishing that paper, we actually released a set. This is probably the first set I'm aware of has the full terrain. I mean, not full terrain. It's a 3x1 vector associated with each turbine unreleased. And this is from one of the wind farm in China. And the work was done by a previous PhD student, now graduated. And we do see some of the benefit. Now, from the data science point of view, there's a challenge of incorporating the terrain, right? As you can easily imagine, all other input to a turbine is a temporarily variant. For different kind of time, they are different. Your power also changing with it. The terrain doesn't. Okay, you probably cut grass a little bit, but that doesn't really affect the terrain, right? The terrain, unless you really have kind of the landslide, otherwise the terrain stay more or less the same. And then there's a question: how you're going to learn the terrain? You cannot just throw the terrain into that traditional learning model because it doesn't change. If you only have one turbine for one terrain, you cannot learn the terrain, the effect. You must have many different kind of turbines over the terrain. So that set of data is public. It's not not included in this workspace, but it's available on my website. And so you guys are welcome to access that data to see if any other terrain model you can build and to explicitly incorporating into the power curve relationship. And the answer is there's not very easy, right? Because of that, the data science challenge, right? We did one of the work before, and Ahmad is exploring other things. And maybe if this is of interest to this group, and I will ask him to come back after the new year to give an update on what he's been doing, and including the previous work. Right. I will include that data set website for that data set, today when I send out the update. So that way you can go directly to download the data set and use however you see fit.
Okay. Thank you. Thank you.
Yeah. Brian, you were about to make some additional comments.
Yeah, but I'm old and I don't remember what it was.
Okay, all right. Any other comments and questions? Oh. Okay, just Christian. No, Christian, please go ahead.
Just a quick question. So this method obviously relies on having a mass data set at the site, but do you think, is there anything from this investigation you think we can take away or apply in a context where we don't have the measurement, like the shape of, like, is there something that could be generalized from this, so to speak?
I think you need to have at least one mast, right? If you don't even have a mast, the other best thing you can do is you have another turbine, but you're going to just use another nacelle anemometer. One of the projects we did with EDP previously, and because they know the nacelle measurement is in the wake, but just assume whatever is in the wake stay in the constant relationship with the free stream wind speed. The problem is really when you modify the turbine itself, that relationship is different. So what they want to do is they want to use a neutral turbine, which the measurement on the nacelle is still in the wake, but with a distance from your tester turbine, just pretend not to be a nacelle, right? By a distance, by a bias. I think it's less ideal. It's I would hope for I visited some of the small wind farm early this year. Even with about 10 turbines, they do have a nacelle met tower on the small wind farm. So I'm wondering in what kind of percentage the wind farm doesn't have even a single met tower.
It's quite market specific, I think. So in many parts of Europe, it's rather uncommon to have even a single met tower. Whereas I know in the US it's much more common.
Okay, let me see. Brian this is the data.
Yeah, I just dropped a link in from open source wind turbine SCADA data sets, and I'm looking at that list, and it looks like down around row 17, 18, 19, there's some data with at least a year of data with a met mast with 40 or so turbines. So that might be worth a look.
Okay.
Or 20 to 30 turbines.
Yeah.
So cool.
And
yeah, I was also expecting that to be the answer. I was just curious to hear if there was anything in the kind of if there was anything at all that you'd taken away in the learnings that you could generalize. But obviously the nacelle transfer functions are hugely different depending on the turbine technology, and
right.
So
yeah, you need to make some additional. I know before COVID, there was a workshop, and in that workshop there was someone from Germany advocating a new anemometer, which is on the cover, the nose cover of the rotor.
The I-spin sensor.
Yeah. So, I was wondering how much that has been deployed, right? I heard it's more expensive than a nacelle anemometer by quite much. I don't know how much it costs. $3,000, something like that. Obviously, that technology, when it's cheap enough, is being used by all the turbines. So you don't really need the I assume it's accurate enough, at least not as accurate as the nacelle anemometer, as if it's not in the wake.
I think it will be. I think it's useful. I think that the problem is a bit like for nacelle-mounted lidars. The business case gets much better if you can integrate it with the turbine control, but then you need the turbine manufacturer on board.
So I gather right now it's still relatively less used for the existing turbine. Still rely on the old technology of the nacelle anemometer, right?
Yeah.
Okay. So maybe if this kind of analysis present a value, and that will promote the European operator to erect a net tower on their wind farm to help to get the better measurement for wind speed. Okay, a couple of things on my side. I need to it won't happen today, but I'm going to work with Hamad, try to clean up the data and find a way to share the data for today's presentation. But in today's update, I'm going to provide a link for the terrain data, which is already public, and there's a paper over there, and if you're interested, you can take a look. We do share the code for implement that method, and so that you can go ahead and go try. It's a statistical method. It's a Bayesian method, and takes some time. Takes some computation to run, but can give you some idea of those kind of problems. Okay, and we are 10:50 my time, and 10 minutes before the hour. And if we don't have any additional questions and comments, and we probably can give 10 minutes back to all the audience.
I have a rather unrelated topic question, but I would like to know if you or others have worked on assessing the effect of blade upgrades or add-ons using LiDAR. Has anyone worked on such topics, or any comments on using it? Because as we know, you have done quite some works, and you have also published a review paper on the challenges in assessing the performance assessing the performance effect of upgrades. So I just want to know if you have done some work on using a LiDAR for this purpose, or anyone else has.
Not me, but I try to understand what is once you use a LiDAR, the wind measurement is more accurate, right? So the method by using the wind measurement is more straightforward, right? Isn't that makes
Yes.
it easier rather than harder?
Yes, it would make it easier. Yes, I just want to know if
Okay.
if there has been some studies done, case studies, or some work that has been published on this, and what are some challenges. And of course cost is a big challenge in this. That is why we prefer to use the side-by-side method or the nacelle anemometer, and then there's also the kernel plus methods that you have developed, and the other methods. But I just want to know if, like you said, it becomes very easier when you use a LiDAR. So I want to know about some people who have worked with it, and challenges and advantages associated with it.
Okay, not me. Anyone in the group?
As far as method goes, the biggest thing when you're doing leading edge stuff is you can get the installation so that you have turbine pairs, so that you've got with and without for side-by-side testing. Because unlike controls related tests, a lot of time you can do a toggle test. You can turn the control feature on, you can turn it off, and you just can't do that with blade edge repairs or blade edge improvements. Same thing with vortex generators. So having those installed pairs with and without for a direct comparison, and then having the data for the turbine that was improved before the improvement, and then you've got side by side before and then side by side after the repair with one turbine as your control is pretty much the only way to do it to get good results.
Yes, Brian. That's also pretty much that we do here at PowerCore. We specialize in making add-ons for blade upgrades, but many times we also find that the correlation between the upgrade and the reference turbine is not as much as we would like. And in that cases we suffer from uncertainty in the results.
Yeah,
so
that's why if you can plan for it, I've actually worked on sites where they've done as many as half the turbines. So it gives you a huge statistical advantage when you think about the size of your sample set.
Yeah. What would you say about not using a reference turbine at all, but using a LiDAR just before and after in the upgrade turbine? So before you put on the LEP or leading edge repairs, do a LiDAR test, and then after you do make a LiDAR measurement and just compare the power curves as such.
That seems reasonable. I haven't been in, I don't have the advantage of, I've only been able to play with LiDAR data on maybe 2 or 3 jobs in my career. It's not that prevalent due to the cost. So I can understand exactly the motivation, but I just don't have the experience to help you out on that one.
I would still suggest that you probably need to account for some other environmental condition, right? Wind speed, of course, is most important if you get that measurement accurately, but the temperature make a difference too. And especially if you compare the period is multiple months, right? And before and after, there could be some difference. The temperature translates to the air density. And but sometimes you don't have the pressure measurement, so the temperature itself is good proxy to use.
Right. That's still there. Yeah, some other environmental effects that's there.
Right.
Yeah, I would add to that. So I haven't verified turbine upgrades with LiDAR data, but I have done it with nearby met masts, which I think kind of gives you a similar kind of thing of a free stream wind speed, as long as you filter for wake-free sectors that's close to the turbine. But generally, I think still side by side, I think is more statistically, I think we get lower uncertainties with a side by side test, or as Brian said, if you can do multiple side by sides in the same side, that gives lower statistical uncertainty than a met mast or LiDAR measurement, because you still have those uncertainties, as Ding says, over other things that affect the physics of what produces power from wind turbines, such as air density, which of course you can partially correct for, but also sort of atmospheric stability effects and so on, which I think a LiDAR can go somewhat to improving on with kind of a rotor equivalent wind speed, but I think it's still not as direct a measurement of power as nearby wind turbine is.
That's right. That's a nice point. So there is stability effects and other environmental effects that a LiDAR can't really completely account for. Yeah, thanks for the points, Philip. Yeah.
Okay, that pretty much concludes today's session. And like I mentioned earlier, and I'm going to cancel the January meeting, and we're going to meet in 2 months, and in February 2025 on February 10th, the same time. Okay, and you have a good day or good evening. Thank you.
Yes.
Thank you.
Thank you.
Thank you all. See you.